Okay, let's dive into this. When most of us first encounter binary search, we're taught it as this simple trick, a fast way to find a number in a sorted list. You check the middle, figure out if your target is higher or lower, and just cut your problem in half. It feels like a neat parlor trick for arrays. But in this explainer, we're going on a bit of a journey. We're taking binary search from that basic array finding trick and transforming it into one of the most powerful, complex optimization patterns in a software engineer's toolkit. Honestly, it's a mindset shift that fundamentally changes how you solve massive computational problems. Here is our roadmap for today's explainer. First, beyond basic binary search. Then, finding the hidden bounds. Next up, the min-max optimization paradigm, followed by thresholds in action, and we'll wrap it all up with the power of complexity. All right, let's jump straight into section 1, beyond basic binary search, looking at the core mechanism. So the fundamental role of binary search is elegantly simple, right? You're basically just having the search space. Amon's AI journal uses a brilliantly relatable anchor for this called the first bad version problem. Imagine you're a product manager. Your team just shipped version 100 of your software, and, well, it's completely broken. Since every version builds on the last, you know that somewhere between version 1 and version 100, a bad update was introduced. Now, you don't test version 1, 2, and 3 sequentially, no way. You test version 50. If version 50 is bad, you know the original bad version is somewhere in that first half. In one single check, you've literally just eliminated half your workload. When we translate this into logic, we get 3 primary steps. Define your left and right bounds, pick the middle element, and then adjust your left or right bounds based on what you find. But, and this is a huge but, there is a very common trap here, picking your midpoint when you have an even number of items. Let's say you have exactly 2 elements left, like indices 0 and 1. If you pick 0 as your middle element and your logic tells you to set your left bound equal to mid, well, your left bound becomes 0 again. You get stuck in an infinite loop, just testing 0 over and over. Mastering binary search means being hyper-aware of this one crucial detail, how your middle element rounds down or up. Moving on to section 2, finding the hidden bounds, because it's really not always about exact matches. Let's contrast lower and upper bound logic for a second. Usually, we look for a specific target and just stop when we hit it. But what if we want the absolute smallest number that meets a certain condition? Well, if our current mid works, we can't just stop. I mean, it might be the answer, but there could be an even smaller valid number hiding to its left. So our new right boundary becomes min itself, and we just keep squeezing that search space to the left until we hit the absolute edge. Which brings us to section 3, the min-max optimization paradigm. This is where the protagonist levels up. Let's look at this exact quote from the source. Find the maximum of the smallest value, or the minimum of the largest value. Let that heavy abstract logic sink in for just a second. It sounds almost like a riddle, right? But when a complex problem asks you to minimize a maximum constraint or maximize a minimum constraint, they are practically screaming at you to use binary search. Let's see how this builds our new optimization paradigm. Take a problem like split array largest sum, where we need to minimize the largest sum among subarrays. Instead of trying to painstakingly build the subarrays directly, we completely flip the script. We just guess the answer. We make our mid the theoretical target threshold. Then we create a super simple, feasible function to test it out. If it takes too many subarrays, well, our guessed threshold was just too small. We are literally binary searching the answer space itself. It's pretty amazing. All right, section 4, thresholds in action, or as I like to call it, bananas, boats, and bouquets. Let's look at LeetCode problem 875 as a fun little narrative palette cleanser. So Koko loves bananas. There are piles of them everywhere, but the guards are going to return in H hours. Koko gets to choose her eating speed. Let's call it K bananas per hour. Now, she wants to eat as leisurely as possible, but she still needs to finish all the piles before the guards get back. So what's the absolute minimum speed K she needs? Rather than trying to calculate the exact speed right off the bat, we just define Koko's search space. The absolute slowest she could possibly eat is 1 banana per hour. That's our left bound. The fastest she'd ever need to eat is the size of the largest single pile of bananas, because she could only eat from 1 pile per hour anyway. That's our right bound. So we guess a speed right in the middle. We run a quick check. At this speed, does she finish in time? If yes, hey, maybe she can go even slower. So we adjust our right bound. We're just having the speed options over and over until we find the absolute perfect pace. Now, the truly crucial point here is how beautifully this applies to other domains. Take the capacity to ship packages problem. We have a conveyor belt of weights and a strict deadline of D days. What's the minimum ship capacity we need? While our lower bound is the single heaviest package, because the ship absolutely must at least hold that. Our upper bound is the sum of all packages, which would be shipping everything in one single day. We pick a mid-capacity, and we just load the ship greedily day by day. If it takes too many days, our capacity mid is too small. If it fits within the deadline, it's feasible, and we try an even smaller capacity. It's just a simple greedy function beautifully integrated right into a binary search loop. Finally, Section 5, the power of complexity. This is exactly why we do this. At the end of the day, it's all about radical optimization. Look at how binary search completely alters your performance metrics. For finding a missing element, a simple linear scan takes O of n. Binary search drops that down to O of log n. For the friends of appropriate ages problem, using a dictionary requires O of n extra space just to track ages. But the binary search approach, it eliminates the counter entirely. It optimizes your space complexity all the way down to an O of 1 constant. In problems like Koko eating bananas, the source explicitly notes that the hours, or the piles, can go up to 1 billion. A billion! If you try to guess Koko's eating speed by counting from 1 to 2 to 3, your program is going to time out and crash. End of story. When you face a maximum constraint of 1 billion, an O log n time complexity isn't just some nice-to-have optimization. It is completely mandatory. To really put that into perspective for a second, if you have a billion items, a linear approach takes a billion operations. But binary search, because you are having the space every single time, log base 2 of a billion is roughly 30. Let that sink in. You literally shrink 1 billion operations down to 30. It's barely a fraction of the computing power, a real game changer. So we've moved from a simple little trick for finding numbers in arrays to a profound way of discovering hidden thresholds in complex systems. It's not just an algorithm anymore, it's an architectural mindset. By defining a simple lower bound, an upper bound, and a condition to test the middle, you can solve seemingly impossible optimization problems in mere fractions of a second. So I'll leave you with this. What hidden thresholds in your own daily logic or your own code could be radically optimized by simply having the search space?